In the early 20th century, the scientific consensus was neat and comfortable. Astronomers believed the universe was static, infinite, and timeless, a vast expanse that was neither growing nor shrinking. So, if you're standing on a relatively young, rocky planet orbiting a totally average star, how do you go about proving that the entire cosmos actually had a beginning? We don't need a time machine to find out. We can rely on cosmic forensics, because the universe left physical traces of its birth. By measuring the physical stretching of space and listening to its ambient background noise, we can completely dismantle the illusion of a timeless universe. In the 1920s, astronomer Edwin Hubble spent his nights aiming massive telescopes at remote patches of the sky, trying to measure the distances to faraway objects. This scatterplot graph from Hubble's data shows recessional velocity plotted against distance. Using spectroscopic redshift data, a technique that measures how light waves stretch as objects move, Hubble realized that distant galaxies are moving away from Earth. As distances increase, the speed of that retreat scales proportionally. The galaxies aren't simply flying through a pre-existing void. Space itself is expanding, stretching the distance between every galaxy simultaneously in all directions. This created an immediate problem. Based on his initial measurements, Hubble calculated the universe was only 2 billion years old. Geologists quickly rejected this, because they already knew the Earth was somewhere between 3 and 5 billion years old. The universe obviously couldn't be younger than the planets inside it. Better astronomical data eventually corrected those early distance estimates. We now know that light from these dense, ancient galaxies has been traveling for immense periods of time, placing the true age of the universe at 13.7 billion years. If space is expanding outward today, running the cosmic clock in reverse leads to an unavoidable conclusion. Everything we see must have originated from a single, infinitely dense point. But that conclusion introduced a completely new puzzle. If the universe expanded from an incredibly hot, dense state, there should be residual heat lingering in the cosmos today. In 1964, Arno Penzias and Robert Wilton were testing this massive horn antenna in New Jersey. They were trying to bounce radio signals off satellites, but they kept picking up a persistent, low-level microwave noise. At first, they figured it was just radio interference bleeding over from nearby New York City, but they couldn't get rid of it. The interference came from every coordinate, bombarding the antenna with a uniform signal from the depths of the night sky. What they had found was cosmic microwave background radiation. As the universe expanded, it cooled, and that initial intense heat faded into a frozen afterglow that today sits at negative 270.4 degrees Celsius. Stumbling upon this omnipresent background heat provided the exact thermal evidence cosmologists needed to validate the Big Bang theory. This illustration shows the COBE satellite, one of the specialized instruments NASA launched decades later to accurately map that cosmic background radiation from orbit. Cosmologists studied these maps, looking for microscopic temperature variations. They knew that tiny shifts in the radiation corresponded to slight differences in the density of matter in the early universe. Those slightly denser patches created a gravitational pull, perfectly matching the mathematical predictions for exactly where stars and entire galaxies would eventually form. This detailed temperature map bridges our understanding of the expanding space and the frozen leftover heat, confirming that we live inside a dynamic 13.7 billion year evolutionary process. This diagram illustrates the universe's evolutionary timeline. Starting on the left, an intense burst of inflation follows the Big Bang. Gravity slowed this expansion for billions of years, but moving right, something strange happens. The expansion unexpectedly gathers momentum, entering a rapid acceleration phase. Cosmologists attribute this to dark energy, an unseen, mysterious effect that causes matter to repel other matter, driving the universe apart faster and faster. While our cosmic forensics successfully cracked the case of how the universe began, dark energy shows that the story of its expansion is far from over.